Worked. Well, welcome to the May program meeting. We have another good program tonight. We're going to talk about Palomar Observatory in anticipation of the fact that it is now open for visiting after all the COVID shutdowns and so forth. It's been doing science for quite a while now, but it's now open for visiting. And beginning the 10th of June, we will recommence the weekend tours. So you can come up for the old standard tours on Saturday and Sunday. So Steve Flanders is the outreach coordinator at Palomar Observatory. He and I are going to share the presentation, and we hope we've got it worked out. And hopefully you'll be impressed with the image that I have on this slide. It shows the dedication of the Hale telescope, and the Cascade is not on there. We're just talking about that, but seeing that big mirror swinging up over all the people gives you a pretty good idea of the size of the whole affair. Okay, you don't want to do that, do you? Okay, as you know, we're having some calendar problems. So I'm just going to throw up a couple of reminders. You know, we do have a star party at West Sycamore on Friday. And on Saturday, it is the fabulous, fun, exciting spring cleanup. And David Wood, it will be firing up the barbecue about 1 o'clock. Come early. I don't think there's going to be any rain, but there will not be a dumpster. So, but be prepared to come and clean up your site and other areas. Ed will be in the observatory working in there. So there are plenty of things to do, and it's very fruitful for you all to show up and help us fix up TDS. Julian Starfest, as you know, Julian Starfest will be held again in August. There's some information about the sorts of events, but I'm really trying to push the volunteering. The JSF people are coming up with a list of volunteer positions. As you can imagine, they have everything on track to get all the permits and get the thing organized, but to pull off the event itself, you know, they just need a lot of help. So if you can volunteer to take a shift or do anything to help them, you'll have some camping opportunities and again, just have a lot of fun. June program meeting will be back in person at Mission Trails and hybrid on Zoom if we can do it. Our speaker is Tim Thompson, who's going to give a talk that some of us have heard on stellar evolution and the origin of elements. He'll explain that slide, by the way, but you know, he's a pretty interesting speaker. He's got a master's in physics, a career in the radio astronomy group at JPL, longtime docent at Mount Wilson, president of the LA Astronomical Society for various periods over the years, and is a tournament chess player. And actually, he's such a good speaker that Mount Wilson will have speaking sessions, and they don't even have to announce the topic. It's going to be Saturdays with Tim, and everybody shows up. So he's a great speaker. We'll have a lot of fun, and I will figure out how to do some type of raffle. I don't have a whole lot of stuff, but I'll raffle off something. I like to pick up some interesting things from the news. And with since Palomar, the theme of Palomar is a brand new instrument that did dramatic new things, and of course is still on the sky and continuing the research tradition. James Webb is amazing us with some of the things that it's doing. And the latest output is imaging the dust cloud around a nearby star, Fomalhaut, trying to figure out planetary evolution from the standpoint of this dusty set of asteroid belts that are around Fomalhaut. Previously, they'd only seen the outer ring with the Hubble Space Telescope and the ALMA radio telescopes, but James Webb in the infrared and near infrared has revealed that there are actually 3 tiers of them. And I've got a quote from one of the researchers: by looking at the patterns in these rings, we can actually start to make a little sketch of what a planetary system ought to look like if we could actually take a deep enough picture to see the suspected planets. Frontiers of astronomy, keep watching. I like to show a product of our imaging group, and David Wood took this and has kindly offered to breathe life back into the group, and we'll devote one of these program meetings to ASIG and imaging and so forth later on this year. But I wanted to put up this rather remarkable image of NGC 6820, and I'll turn it over to David to explain how he did it.
So this is an object that almost nobody images for whatever reason. It's about 3 degrees west of the Dumbbell Nebula. This is about 40 hours of narrowband imaging. It's actually 37 hours, pretty much split between the HO or HAS2 and O3. If you're an imager and follow anything that's going along with PixInsight, there are some extraordinary new tools that are coming out. At least 3 of them are all based on AI by Russ Croman, and they've all been put to good use in this image. Likewise, there's a gentleman by the name of Bill Blanchard that seems to believe that he can do anything with pixel math, and his pixel math expressions that you can use and download off the web also work tremendously well. So this was a reprocess of something I did a couple of years ago just to run through and see what you could pull out of it. Nowadays, the stuff is so good, you can immediately after doing a histogram stretch, you can pull the stars out and then work separately on the nebula and work separately on the stars so they don't get blown up and stuff like that. So it's becoming a new fun game out there to do a lot of processing on.
Yeah, thank you, Dave. This is he's been showing us all this for the last week or so, and it's unbelievably impressive. Getting on to the meat of the program. I have a slide about Steve Flanders. He's in both of these images. On the lower right image, he has actually participated in reilluminizing the 200-inch mirror. That is Steve at the far left, wearing the denim Palomar shirt. And the upper left, this is Steve coming into the plate room that houses the glass POSS plates from actually just last Saturday. So Steve is the outreach and event coordinator for Palomar Observatory. He has a master's degree from Harvard in the history of science. And as I said, we're going to split the talk. I'm going to have him start out and talk about the history of Palomar Observatory, and I'm going to pick up with some of the science and the current instruments and what they can do. If it's okay with everybody, hold the questions until the end of each of the individual sections. And with that, Steve, the floor is yours.
Well, thank you, Ken. Thank you very much.
I can get rid of mine.
And I will share my screen when there we go. If I remember how to do this.
Yeah, I was just trying to figure out what button myself.
Exactly. There we go. Slideshow. And
You've got the LA Public Library.
I got the wrong one. Hey, hang on just a second there, friends.
He had this all practiced there, Steve.
Oh, come on. Give me a break. Well, okay. Hang on, we'll get there. Yeah, I did go to the wrong place. Well, that's an embarrassing way to start off, isn't it?
It's kind of PowerPoint usual or Zoom usual, isn't it?
Well, sometimes, yeah. Okay, let me try it again here. See if we can't do better this time. That look closer? Maybe.
Kind of looks like it.
That looks like it. How about that?
That's it.
Okay. Everybody got the right, we got the right presentation. And hello,
Great,
excuse me?
looks great.
Please, I missed, please tell me that again.
This is Seppi. It looks wonderful. Thank you.
Well, thank you. Spent a little bit of time on this one anyway. And, you know, hello and good evening to everyone from San Diego Astronomy Association. It's a pleasure to be here tonight. Thank you for letting me join your meeting and asking me to speak with you. Yes, I run the public outreach program at Palomar Observatory. Best job I've ever had. Done it for about almost 10 years now. And then a couple of years as a volunteer before that. This evening, I'd like to spend some time talking about the building of the observatory, its history, building of the 200-inch telescope. When I'm done, Ken will talk about the science of Palomar Observatory. Palomar Observatory is owned and operated by the California Institute of Technology. The Hale telescope was built with a $6 million grant obtained from the Rockefeller Foundation in 1928 by George Ellery Hale. Hale died in 1938, and when the telescope was dedicated in 1948, it was named in his honor. Born in 1868, Hale graduated from MIT in 1890. He was an astrophysicist and a solar astronomer. He is considered by many to be the founder of modern astrophysics. Hale invented the spectroheliograph, and he discovered that sunspots and solar prominences originate in magnetic disturbances near the sun's surface. Hale was a founder of Caltech. And he had a talent for getting money out of rich folks for big telescopes. He built the largest telescope in the world 4 times. And in each case, he did it using other people's money, the Carnegies, the Rockefellers, and others. Hale's first 3 telescopes are shown here. The Yerkes 40-inch refractor, the 60-inch reflector at Mount Wilson, and the 100-inch Hooker reflector at Mount Wilson, completed in 1917, probably the most productive scientific instrument of the first half of the 20th century. But Hale always wanted more light. He was always looking for the next larger telescope. In April 1928, he began a campaign that he hoped would generate interest in his proposal for a new and larger telescope. He told a simple story. He said, we are on a voyage of exploration and discovery, and transported by our great telescopes, we are venturing upon a universe vastly larger than anyone had supposed even a decade earlier. A larger telescope, he argues, quote, could effectively be used to extend the range of exploration further into space. Well, the governors of the International Education Board of the Rockefeller Foundation found Hale's arguments to be compelling. In June 1928, they awarded $6 million to Caltech to fund the construction of a 200-inch astronomical reflecting telescope that would be, in the words of the grant, as complete and perfect as possible. From the beginning, Hale knew that the 200-inch mirror would be the pacing item for the entire project. The fabrication of a 20-inch glass disc was seen as a major engineering challenge, and in 1928, no one knew if, in fact, it could be done. Well, after several failed attempts by General Electric Corporation, the job of making the 200-inch disc was taken over by Corning Glass Works and the company's chief scientist, George Macaulay. After a series of successful tests, Macaulay began preparations for pouring the 200-inch disc. In this image from late 1933, a frame to enclose the mold is nearing completion in the Corning factory. Corning Corporation marketed a range of consumer products, baby bottles, test tubes, and the like, made from their patented formulation of borosilicate glass, which they copyrighted under the trade name Pyrex. Having a low coefficient of thermal expansion, Pyrex was attractive to Caltech's telescope builders because it does not change shape significantly as the temperature changes. By late March 1934, construction of the mold was complete, and on the 25th, Macaulay and his employees began filling it with molten glass. Corning invited the public into the factory to witness an event of national significance to many people then living through the Great Depression. Building the 200-inch telescope had come to represent an assertion of America's industrial competence and scientific leadership. Starting at 7 a.m., workers began scooping 2,700-degree molten glass from the melting oven using ladles that moved on overhead tracks. Each ladle held 750 pounds of glass, and once filled, workers rolled the ladles to the mold, as you see here. Each pour was followed by a refill at the melting oven, and so the process was repeated until the mold had reached its capacity of 20 tons of hot Pyrex. This first pouring failed due to problems with the mold. But although the first disc seen here was unusable, the failure was not with the disc itself, but rather was with the structure of the mold, a problem that in fact was easily solved. Importantly, the failed disc provided proof that Corning could successfully produce a 200-inch Pyrex disc. With that understanding, Caltech approved a second pouring, which Macaulay scheduled for December 1934. And on the 2nd of that month, a few Caltech officials joined a group of Corning's managers and workers on the factory floor. No one else was invited, and no public announcements were made. Again, the pouring started at 7 a.m. and continued until 20 tons of molten glass had been ladled into the mold. When the ladling was complete and no problems were apparent, Macaulay moved the still molten mirror blank into the annealing oven. It remained there and cooled slowly. After 10 months, Macaulay removed the disc and carefully examined it for cracks and deformations. When no major defects were found, he and George Hale judged the second pouring to have been a success. Finally, 2 years after the first attempt, Corning placed the disc in a protective steel container and drove it from the factory across town to the rail yard. It was then raised to an upright position and placed on a freight car, specially built for the purpose by the New York Central Railroad. The following day, with its bulletproof metal container painted white and adorned with a bit of advertising, the disc started off on its 16-day rail journey to Caltech's optical lab, Pasadena. Moving at 25 miles per hour and stopping every night, the train traveled a route that had been carefully chosen to avoid low bridges and overpasses. The rail journey also marked a major cultural event. In towns and cities along the way, schools were dismissed so that students could go down to the railroad right-of-way to see the train as it passed, carrying its unique and historic cargo. Train finally pulled into the rail yards at East Pasadena on April 10th, 1936. The disc in its container was unloaded from the rail car and driven to the optical laboratory at Caltech. This is the crew of Caltech's optical lab under the direction of the chief optician, Marcus Brown. They will spend the next several years grinding, figuring, and polishing Corning's 200-inch Pyrex mirror blank. The Observatory Council at Caltech thought the job would take 5 or 6 years to complete. And in the spring of 1936, as work on the mirror was starting, progress was also being made on other elements of the telescope project. In fact, the planners and engineers needed land on which to build. And within 2 months of Macaulay's declarations regarding the successful disc, Caltech began purchasing land for the observatory on Palomar Mountain. From the beginning, finding a site for the telescope had been a matter of great importance. The site selection committee had moved quickly to identify a dozen or so mountain locations where conditions of weather and of seeing might be suitable. Caltech graduate students and a few local residents were hired to take meteorological readings and evaluate seeing quality. For the work, they were issued identical 4-inch refractors like the one above. Palomar had good seeing conditions, very dark skies, and a broad plateau at 5,600 feet, an ideal location on which to build the needed infrastructure. William Beach, a rancher, owned a large portion of that plateau. On September 22nd, 1934, a meeting was held in his cabin. He and several other landowners met with representatives from Caltech, the County of San Diego, and the Cleveland National Forest. During the evening, agreements were signed that transferred ownership of 200 acres to Caltech, 120 acres from Beach, 40 acres from the Cleveland National Forest, and a further 40 acres from 2 other landlords. Additional purchases would be made later to a property that now totals 2,200 acres. Yet for several months, the land deal had been in jeopardy because there was no serviceable road to the site. This contemporary image suggests what roads on the mountain were like in 1934. Fortunately, the Board of Supervisors of the County of San Diego stepped in and agreed to build a hard-packed gravel road using public funds. Unfortunately, the county quickly ran out of money, and early in 1936, the California Department of Highways took over the project. Canfield Road was completed by the state in June 1937. The Highway to the Stars, now County Road S6, runs all the way from Del Mar to the observatory. Well, workers arrived, excuse me, soon after the agreements were signed. Excuse me, try it. And clearing and leveling operations began in the summer of 1935. A workers' tent city is seen in the foreground with administrative buildings on the left. The light colored patch of ground at the center right marks the location chosen for the 200-inch telescope. Of course, the observatory needed all the facilities of a small town. Roads were built and graded. An administrative building was constructed to provide space for offices and for a number of maintenance functions. Wells were dug and pipes laid to the water tower and the dome. On June 30th, 1936, footings for the foundation of the dome were in place. This is the light colored patch of ground we saw in an earlier, just a few moments ago in an earlier slide. With the footings in position, the telescope's massive base was erected at the center of this circle. Seen here on September 28th, 1936, this structure now supports the 530-ton telescope on the observing floor above. Consolidated Steel Corporation of Los Angeles built the dome. Here, the dome's central arch is nearing completion. The arch will carry a 60-ton crane needed to bring parts of the telescope up to the observing floor. And by early fall 1938, the walls and the dome were complete, as were many of the observatory's ancillary structures. The grounds had been prepared, and at least the dome was ready to receive the mounting and tube of the 200-inch telescope. Well, all this was going on. The Westinghouse Corporation was working on the truss tube and the mounting of the telescope. In this photo, workers stand inside the ring that will tie the members of the truss tube together at the lower end of the structure. Westinghouse Corporation was chosen to fabricate the mountings and the tube, and in large part, it seems Westinghouse was probably the only domestic firm that had hydraulic presses large enough for the job. In this image from the fall of 1936, the lower truss ring we saw in a previous slide is being forged in a press in the South Philadelphia factory. Westinghouse boasted about the immense scale of the undertaking by publishing images such as this. Seen on July 8th, 1938, the mount's east-west support arms are joined to the yoke bearing at the south end. But the truss tube was completed before the rest of the mounting. To celebrate its completion, Westinghouse held a dedication ceremony in the factory on April 30th, 1937. Among the invited dignitaries, the presence of one guest in particular drew the crowd's attention. Albert Einstein attended. As far as we know, this event represents his only involvement with the 200-inch project. As manufacturing and annealing operations were completed, Westinghouse began moving parts from the factory down to ships waiting at docks in the Delaware River. As they were loaded, the ships sailed down the East Coast, through the Panama Canal, and north to the port of San Diego. Here, a section of the horseshoe bearing is lifted from the hold of a freighter named the American Robin and secured to a trailer for the trip to Palomar Mountain. The new road, Canfield Road, was opened by the time parts of the telescope began arriving. In this image, two tractors are linked together to haul a section of the horseshoe bearing to the observatory. One of the tractors has broken down under the heavy load. As they reached the observatory, parts were staged at the road junction on the west side of the dome. Here, the prime focus ring is about to be moved into the dome on the ground floor. Then, the order required for assembly parts were raised from the ground level to the observing floor. Here, a section of the horseshoe bearing is being raised through a hatch in the observing floor. In this image, taken January 6, 1939, the west arm of the yoke rests on a temporary scaffold as the east arm is raised into position. On February 17th, the yoke is complete. The telescope's tube will be installed between the arms. And at the end of the year, the building and the dome are complete, as also is the structure of the telescope inside. While adjustments to the telescope's control and tracking systems will continue for quite some time, the telescope is now ready for the mirror. And Marcus Brown and his team of opticians, began work on the mirror in April 1936. They used this machine in the optical lab to grind and polish the mirror's paraboloidal curve. Driven in circular motions around the disc, this grinding tool did the heavy work of removing 5.5 tons of borosilicate glass from the upper surface of the disc. And the work went well. In the summer of 1941, Marcus Brown assessed the mirror's figure, formed a knife edge test, and the test showed that his crew had successfully shaped the surface to within a first-order approximation of a perfect paraboloid. Everything was on schedule, and the end seemed to be in sight. Well, World War II, however, intervened, and the mirror project was put on hold at the end of December 1941. The work did not resume until December 1945. At that time, Brown gathered his workers, and in less than 2 years, the job was complete. Marcus Brown was well satisfied with what his crew had accomplished, and to commemorate, he scratched his name into the glass at the edge of the Cassegrain opening. Then everyone helped to prepare the finished mirror for its journey to Palomar Mountain and the observatory. The journey to the mountain began on the morning of November 18th, 1947, when the mirror left the optical lab in Pasadena, pulled by a 22-wheel tractor trailer owned by Balea Truck Company. Almost 12 years had passed since the 200-inch Pyrex disc arrived at Caltech. In that time, Brown's crew had used 31 tons of rouge and abrasive compound and had spent 180,000 working hours grinding and polishing the glass. Now carrying the finished mirror, Balea's truck turned east on California Street before heading south to join Highway 101 and later the Coast Highway. After passing Mission San Juan Capistrano, the caravan reached the Coast Highway that afternoon at 12:30 p.m. and drove through Camp Pendleton 2 hours later. Then the line of cars and trucks headed inland at the junction with State Route 78 in the city of Carlsbad. They soon reached Escondido, their stopping point for the night. The journey resumed. The vehicles left the hotel in Escondido at 5:15 in the morning. Seen here, the driver, Lloyd Green, has stopped the lead truck on Valley Center Road to allow Balea employees to perform mechanical checks prior to beginning the ascent of the mountain. Although a warm, sunny fall day had been predicted, the drivers met wet, cold, and icy conditions as they started up the mountain. Byron Hill, the first superintendent of the observatory, stood on top of the box for the entire journey. With one truck pulling and 2 trucks pushing, he shouted instructions to the drivers so that they would all shift gear in unison. Despite the conditions, the mirror arrived at the dome before 11 a.m. on November 19th, 1947. Driving the lead truck, Lloyd Green backed the mirror in through the big doors on the west side, where it was later unpacked and lifted to the observing floor. Soon after the mirror arrived on the observing floor, a coating of reflective aluminum was applied to its upper surface. With this new coating, the mirror was mounted in the telescope and made ready for the start of a long series of optical tests. Well, the optical tests quickly showed that the fabrication and shaping of the glass had not gone as planned. The mirror did not sag at its edges, as had been predicted. Its edges were too high, and many months of work would be required to bring them down. But an important event occurred during these months. Caltech dedicated the telescope in a ceremony on June 3rd, 1948. That day, hundreds of invited guests sat under the telescope to hear Caltech President Lee DeBridge announce that this powerful new instrument of science would be named the Hale telescope. George Ellery Hale had passed away 10 years earlier. He never saw his greatest accomplishment. And the 75th anniversary of the dedication will be commemorated at the observatory in less than 3 weeks. And through this period, the opticians continued to work to correct the defects in the figure of the mirror. While they wanted to keep making gradual improvements, eventually the impatience of the astronomers overwhelmed their careful craftsmanship. On the evening of January 26, 1949, Edwin Hubble was given the honor of taking what is considered the Hale telescope's first light image. He made a 15-minute exposure of NGC 2216, an object also known as Hubble's variable nebula. Through spring and summer of 1949, balance and tracking problems were solved, and a major issue with the mirror support were fixed. Finally, after 2 nights of tests, Ira Bowen, director of Palomar and Mount Wilson observatories, declared that science operations would begin on the night of November 12th, 13th, 1949. Milton Humason, Hubble's assistant at Mount Wilson, was the first astronomer to use the 200-inch Hale telescope. Science programs began with Humason's observations that evening in November 1947, and the Hale telescope has remained in service ever since. It now supports the work of professional astronomers on average 300 nights a year, and it has been doing so for the last 74 years. George Ellery Hale had a motto: make no small plans, dream no small dreams. And I feel like, and thank you very much. Thank you for asking me to talk. And I will point out that the observatory now is open to the public from 9 a.m. to 3:30 p.m. daily, and we will resume public weekend tours on June 10th. Thank you very much. Questions? Questions?
I do have a question,
Sure, please.
and it has nothing related to astronomy per se, but I was thinking that the first casting and the second casting, were they insured? And if so, for how much? Because the first didn't work, boom. And so you had to do a second one, and I'm sure they had to be insured in some way, shape, or form.
I don't know. I don't think so, because all of this, all the money to do the castings, to, you know, the first failure with General Electric Corporation earlier, this all came out of the $6 million. So I don't believe they operated that way then.
Okay, because that made sense to me, considering the amount of money that was spent on this. I would also imagine money would be spent in case something happened, like it was being dropped, or if the weather was a factor and it cracked, etc. Because of course we're all litigious happy out here in this time frame. So I was just wondering about that, with all the money being spent, whether or not there was such a thing as it being insured in case it was broken or destroyed, or some other, something else happened. But thank you. That answers my question.
And you know, even now, I don't know if this is exactly relevant, but you know, even now, Caltech considers that, well, it's a big player, and Caltech is even now self-insured. So that's basically what they were doing back then, I think. That, I don't, other questions?
Peter, go ahead.
Great talk, Stephen. You sort of implied that the opticians were not given the chance to make the mirror as good as it could be. So is that true? You know, was it sort of left not quite perfect? And in the end?
It was, yes, it was left not quite perfect. Exactly how good they got the final figure, I've heard various figures at various times, but the point is that the figure they obtained is much better than the resolution that could be obtained with average seeing, with any seeing conditions here on the mountain. And that
Okay, so it's good enough. is what you're
exactly,
saying.
and that was the rationale they used at the time to put an end to the work of the opticians up here. And you know, we rarely get seeing better than 1 arc second, rarely get sub-arc second seeing, and the mirror resolution is, one way or another, is a lot better than that.
Right, and I mean, they would have had the opportunity over the years if it was a problem to have fixed it, I assume. So, okay, thank you.
Hey, thank you, Peter.
Philip, you got one?
Yeah, and I actually follows on very well from that. It looks like you said the mirror arrived and it was illuminized, so I presume it's an illuminization vacuum facility where the mirrors drop down into it. It was illuminized, and then it looked like it was mounted, and then they found that the edges of the mirror were still too high. It didn't flex the way that they thought. So did they subsequently have to, with polishing, basically polish off that first aluminum layer? And did they do that in the tank, or did they do that while it was mounted?
Well, the aluminum is removed with a series of applications of an acid bath. It just pour acid on and the aluminum is gone.
But it doesn't eat the glass, right?
We hope not. We don't think so. So far, we haven't found that it has. But yes, when they were doing corrections to the surface, they had to do that against the native glass without the aluminum coating on it. And the optical tests they did, they used a Hartmann test. These tests were done against a mirror that had no reflective coating on it, which, you know, the basic surface itself reflects some portion, some part of starlight, and that was sufficient for doing the tests that were done on the observing floor.
All right, thank you. And so, well, Kin might actually be able to chime in here. The illuminization process, is it pretty much the same today as it was that very first time?
Well, it's certainly the same in the sense that they're using the same equipment. There's a great big vacuum chamber back on the west side, and they have diffusion pumps that will draw a vacuum of, let me see, 10 to the -7 torrs, and they're using essentially the same process that John Stone invented in the early 1930s. He invented it for Palomar, but it was first used at Lick and then at Mount Wilson to replace their aluminization, their silvering process. And then it came to Palomar Observatory when the telescope was ready.
And all the mirrors on the mountain get illuminized in that same place, including the secondary and for the other telescopes, I would imagine.
Well, same place, same location roughly.
Yeah.
There's up on the observing floor, there's this huge vacuum chamber that we use to reilluminize the 200-inch mirror. On the ground floor below, there is a second vacuum chamber,
Oh, okay.
smaller, and that is used for all of the other mirrors on the mountain. We reilluminize the 200-inch mirror. Right now, we're doing it every 2 years. We'll be doing it in, excuse me, October of this year. Other mirrors are done on different schedules. The mirror of the 48-inch Samuel Ocean telescope is done every 5, 6, maybe 7 years, but that telescope is not an open tube. So we don't, the mirror doesn't get fouled
Right, right.
as one open to the sky.
All right. Thank you very much.
Thank you. Other things?
You've got some questions. Kurt Klinghorn in the chat asked, obviously light pollution then was much less than it is now. How has Palomar dealt with that?
Well, went over pretty quickly, but you know, when they bought the land in 1934, this was one of the darkest spots in the country. Hard to believe now. The horizons are getting brighter and brighter by the month. I was out one night a few days ago, and we're getting more and more light, particularly from the northeast toward Palm Springs. And what we're doing, first of all, the sky within 45 degrees of the zenith is in reasonably decent shape. But one of the main things we're doing is emphasizing investigations in the near infrared, which isn't bothered by what we usually call light pollution, and so far that's been a key strategy to dealing with the problem. We've kind of lost the battle of the spread of light around the observatory, unfortunately.
Pete Shearer asked, interesting question. Telescope and mirror vendors often advertise special mirror coatings that boost the efficiency above that achieved by aluminum alone. I assume they would also be used at Palomar. And I'll take a swing at that and say, no, I think they have their own process. And, you know, they're comfortable with the repeatability of it. But you may have more.
Yeah, they put no coatings on the mirror. They have, you see, here we have partners, we have contracts that say the mirror has to reach a certain reflectivity, and we're able to do that quite consistently from one illuminization to the next. We have to do it every 2 years, more frequently than we might otherwise, but that's how we keep up the reflectivity of the telescope.
Okay, Peter Lee asked, and you know all about the various secondary mirrors. Who did the secondary?
Well, in the Hale telescope, there are 3 secondaries, one for Cassegrain focus and 2 for Coude focus. The glass came from Corning, of course, And the optics, the grinding and polishing, and that was all done at the optical lab. Same is true for the mirrors and corrector plates of the 48-inch Samuel Ocean telescope. Other things.
Yeah, Steve, is there a movie that covers the construction of the entire scope? Is there, that basically takes all the stuff you have and puts it all together?
The best one I know of is the documentary, and forgive me, I forget the names of the people who put it together. The documentary is called Journey to Palomar, and it covers probably at a relatively high level. It covers the work both at Mount Wilson and at Palomar. It's a really very special film.
Aziz asked what happened to the optical lab in Pasadena. Is it still there? The building's still there, but it's not being used as an optical lab.
Yeah, they stopped doing optics. Well, I'm not sure when they stopped. It was late 50s or 60s, and yeah, the building is there, but they don't do that kind of work so much anymore.
And Georg asked about AO, but I'll cover AO in
Okay,
the second part.
well, Ken, you probably want to.
Oh, you're doing fine.
Well,
No, you've got a lot of fascinating material, and you've really worked hard on this talk.
yeah, but we agreed to share.
Okay. So I will share my screen,
Okay.
and hopefully it will come up. And this is a rather daunting task to cover Palomar science. And I've got some slides that have been approved by Caltech, and I keep updating them about every 3 months. But even so, it's maybe not complete and probably idiosyncratic. But I always like to tell the public, the mission is science. And number one is what you think. Conduct compelling scientific investigations in astronomy and astrophysics. And basically, that's what I'm going to try to cover to some degree here. Also provide facilities for astronomer training. It's if you've ever seen a teaching hospital, they coin doctors, and this facility coins PhD astronomers, some of the best researchers in the world. A third that you might not think of until you realize how robust the instrument is itself. It was extremely well built and will take a huge amount of additional weight. So increasingly, it supports development of the state-of-the-art astronomical instruments made by JPL, Caltech, and others. So you would do a proof of concept and get some science results on your instrument at Palomar and be able to do all the integration and all the testing and so forth, and then take the instrument to another telescope, perhaps a bigger one like Keck. And of course, share the observatory's research mission and tradition, which is why Steve is there and why they're open and do all the tours. This is kind of a canonical slide. If Mount Wilson was the most productive scientific instrument in the first half of the 20th century, one could make a case for Palomar for the same thing at the second half. We might have a little bit of arm wrestling with the nuclear physics guys, but look what they did. They built a bomb. And we tried to understand how the universe works. Alan Sandage and Fred Zwicky, hugely important people who really understood the fundamental structure that we only see a small portion of the actual material in the universe. Martin Schmidt on the right hand, that I remember this Time magazine article. I was getting Time magazine at that particular time. Martin Schmidt discovered got the spectrum of what would become known as a quasar. And there are, I think, about 5 of them had been discovered by radio astronomers. And radio astronomy had come into its own after World War II with all the radio equipment. Okay, you've got this big optical telescope. We think we know where the source is. Tell us what it is. And Martin Schmidt was able to get a spectrum up at prime focus with a prime focus spectrograph that's now in the Smithsonian, by the way. And it was very highly redshifted. And that's a little bit of a problem because it seemed to be a star, but if it was highly redshifted, it had to be much further away. So how come it's so energetic? Well, it's really the active nucleus of a galaxy caused by a supermassive black hole. And of course, you know, the famous star stuff came from Palomar under Willie Fowler, the Babbages, and Fred Hoyle, working on how elements are synthesized in stars. And actually, Tim Thompson's going to talk about that at our next program meeting. There's always the Green Comet. There's the fact that Pluto's not a planet, that I just have to rub that in. But probably the first really big thing, even before my first bullet, is Alan Sandage and Walter Baade using the big telescope to refine Hubble's calculation of the Hubble constant. With a much bigger, Hubble relied on the standard candle of the Cepheid variable stars, whose the period of oscillation was directly linked to the absolute magnitude. Turns out with a bigger telescope, you realize there's not one population of Cepheids, there are 2 different populations. And when you work those numbers in, you came up with a good approximation of what we accept as the modern expansion of the universe. There's the event horizon image of just an area of the black hole. The status, it's on sky every night, an average of 300 nights a year, based on weather and engineering. Observing can be remote or local. Some instruments, people like to come to the observatory. They like the Palomar experience and so forth, but you can collect the data and control the instruments remotely, although the telescope would be manned by the staff while you're doing it. If you're not putting new instruments on your telescope, your observatory is dying. And that's certainly not the case for Palomar. There's been work to upgrade the adaptive optics system, although it's been having a few problems lately. There's a new prime focus imaging camera. There's a new radial velocity spectrograph. There's the 1 meter plane wave for an IR survey. There's this unique little flare scope, which I think is a 24-inch plane wave in this sort of a clamshell observatory that's designed to work with, in cooperation with Owens Valley Radio Observatory, to detect the optical transients of flares that are detected by the radio system. They're even doing an experiment. The deep space optical communication is a laser link. It's going to be deployed with the Psyche mission. The idea is to do laser comms to augment the deep space network in the vicinity of Mars. And of course, there's a new adaptive optics system coming on that will operate in the UV spectrum. And why that's important is, rather than, we no longer use the high energy laser system that would produce an artificial star up about 5 miles. That was tricky. It took a lot of coordination with the satellite community, as well as the airlines, and people with radios had to be stationed outside. So we use natural guide stars, and I'll talk about that But this new AO system in ultraviolet comes out of an experiment that was done in Palomar. So it can be used all the time because it's not going to affect aircraft or satellites. Every once in a while, I do a little monthly snapshot. It's a general purpose observatory. And this is a snapshot of the 200 from some arbitrary month. And I just bin the different projects that they were doing. And this particular month happened to be monitoring galaxy status and formation. There was some survey follow-up from the Zwicky transient facility and the director's option. Imaging brown dwarf atmospheres, you know, they're very bursty. Looking at star formation, AGNs, X-ray binaries, black holes, compact binaries, and one night they got for engineering. Every month would be different. That just gives you an idea that, you know, it's an instrument in very high demand by a whole variety of different researchers and users. The telescopes at Palomar, Steve talked about the 200-inch, the big eye. Newtonian telescope, although it's got a Cassegrain focus and other foci. That's kind of the hallmark, but in fact, there is a 48-inch Schmidt, either telescope or camera, depending how you want to call it, that can take very wide field images. It's operating completely robotically, and it's teamed with the 60-inch Ritchie accretion in this construct called the Zwicky Transient Factory. And factory is the operative thing. Let's pound the sky, observe every part of the sky every 2 nights, the Milky Way twice in 1 night to look for things that change. This is kind of a new paradigm in astronomy, very high cadence astronomy. And Palomar Observatory has really been on the forefront of that effort. Same thing will be happening in the infrared with a smaller telescope, Gattini, and then a larger 1 meter plane wave telescope called Winter. And of course, you already saw the little clamshell of flare scope. So
real quick to interrupt you, Ken, we've had a couple of people asking, what does AGN stand for?
Active galactic nucleus. So in other words, black holes, the bipolar jets and things like that. Okay. Usually I use this for the beginning of a little bit of a tutorial thing with the public, but remember, it was designed for imaging always. Nobody was looking through the telescope, taking detailed drawings and so forth. And it was all done in the era of hypered glass photographic plates. And there's this kind of doofusy looking guy looking at one of the large plates that happens to be one of the 14 by 14 plates from the Palomar Observatory Sky Survey. There were 2 of those done. One in the 50s that surveyed the entire northern hemisphere, accessible from Palomar, and there was a corresponding Schmidt down at Sidling Springs in Australia, and they mapped the sky. That was a very useful tool for astronomy, and it's still available. You can still, you know, reference it. It's been scanned. You can get it in software. They repeated that whole thing later, and now. But my point is, if we're still alive, we still have the best modern instruments, and software is becoming an increasing part of that. Key tools, obviously direct imaging, just like the Hubble's Nebula. Take a picture, try to figure out what's happening. You can do photometry, and we've seen lots of presentations on how to discover exoplanets with through light curves and so forth. Photometry is the changing nature of the light. Spectroscopy, breaking the light down into its constituents and associating those frequencies of light with the atomic structure and elements. Some of the new things, there was a question about adaptive optics. Yes, in fact, you can beat the seeing with adaptive optics. And you need that for a very important thing that I'll talk about. In network telescopes, it's not just all one telescope sitting, all by itself doing lonely research and, going home and writing papers and so forth. Now there are a whole series of collaborative telescopes, and communications is such that even on the mountain, if the ZTF discovered something of extreme interest and the 200-inch was being used in a mode that particular night that interruptions were allowed, you could discover something in a very short time on the ZTF. Something went bump in the night, something exploded. It's a early detection of a supernova, maybe in under 24 hours, and go get a spectrum with a 200-inch. Time domain astronomy, very high cadence like the ZTF. We're not just studying static things anymore. We're trying to understand their dynamic characteristics. Multi-messenger, that's like the radio astronomers and the optical astronomers teaming up to get more data on a particular object. And yes, in fact, gravitational wave astronomy is part of the multi-messenger. And machine learning and AI, if we're going to do it faster and better and have very stringent pipelines, we're going to have to use adaptive optics to be able to help us out, because the human just can't do the interpretation fast enough. And that's part of my last bullet, progress in AI to analyze complex data sets. In the old days, there were a lot of images taken that were actually never really thoroughly explored. And, that analogy is breaking down. Speaking of analogies, the racing car analogy versus computer technology, using CCDs on a modern telescope like Palomar, the CCDs are probably a good 100 times more sensitive and therefore efficient than the old hybrid glass photographic plates. So look at computers are faster than they were in the 60s by some factor that's somewhere between 100 and 1,000. CCDs are faster, but your poor old racing cars, they're not going 100 times faster than they were back in 1947. Just give you adaptive optics. Let's see if I can get this to run. How do you do science with this? You see the star, and we've all seen this effect. Okay, now you're going to see it. We've all seen what the stars do, thanks to the turbulence of the atmosphere, obviously at different altitude layers, but you get this cumulative effect, and wait till you see the star jump. I just love this. Go ahead. Yeah, there it goes. Golly. So how do you do science? So the atmospheric limited resolution is about like that box. And to scale, the actual star size is as illustrated. So, how do you bridge that gap? And of course, you do it with adaptive optics. Before and after, this is off at Keck, by the way. So with adaptive optics, you see the airy disk around, to a double star system. It just looked like some kind of spill paint without AO, with native resolution, blurred by the atmosphere. Maybe a little bit better example, faint companion stars. And this is going to be very analogous to imaging exoplanets, which you can do only with the adaptive optics system. You'd never be able to dig a planet out of that blurry haze on the left. The only point I want to make, I don't want to go into this because I don't have time really. The only point I want to make is Palomar gets high performance out of the adaptive optics system with a natural guide star, no more, laser projections of an artificial star. And that's, you get very good performance just to natural guide stars, of about magnitude 17 and brighter. And that works out very well for exoplanets. Performance falls off a little bit if you go to magnitude 18 and so forth. There's the adaptive optics system. It is an extreme AO system. And of course, it was really designed to validate exoplanet candidates from satellite systems like, Kepler and TESS and others. That's it in the big black box. That's at the Cassegrain focus. You can kind of see at the top of the image, you can see the bottom of the mirror cell, and that dark blue instrument is a system called Pharaoh that was designed to work with the AO system in infrared. It was recommissioned following a major upgrade, and I think they're going through another recommissioning period now. But that's lower, the image really shows an exoplanet detection, and if you look at the scale from 0 to 1 arc second, so it's about -1 to +1 arc seconds across, you can see the central star has been blanked out by a coronagraph. And it's a very special instrument. They take a great deal of pride in this. The stellar double coronagraph, or the super duper coronagraph as it's called. An earlier system called 1640 was actually able, this is another image on the left, with a multiple star system, a planetary system around a star that's been blanked out. But they were actually able to derive spectral curves from the system. And you can just tell by inspection right away, without going into any deep science, that yes, and the atmospheres are all different. What's going on here? This has been decommissioned, and some of the parts were included in Parvi, which I'll talk about, I believe. Next slide. Yeah, this is an adaptive, an AO system that is fed by single mode fiber from the 200-inch. It's down in a room off of the basement, but it is a diffraction limited spectrograph. High resolution, a shell spectrograph. I think the R value is something like over 100,000. And it is really designed for exoplanets around low mass and smaller stars. And it can actually detect radial velocity changes of about 1 meter per second. Let's go into time domain astronomy a little bit, because I really like the hardware. The old 48-inch Schmidt telescope that's been rebuilt a number of times, actually. They put in, it did the original Palomar Observatory sky survey. That was repeated. They added a new corrector plate to it. I think it's on the 3rd or 4th camera. The Schmidt camera is down at the lower section with all of these individual CCD blocks. You know that by nature, the Schmidt imaging surface is curved, so all these things have to be shimmed to give a good curved surface. And the top picture shows some of the Caltech technicians actually working inside the telescope. But the beauty of it is that it takes an image with this new CCD camera and a new corrector plate of 47 square degrees, and it can take a frame a minute at 576 megapixels. Has a fairly complicated control structure to control the different banks of CCDs. But these images taken, one at a time in a sequence, changing filters, these images are data linked up to Caltech, and that's where the adaptive optics or the artificial intelligence comes in. These are automatically blinked with AO systems, all written in Python, and they generate something like 1 million alerts per night. That's down selected. Good candidates go to the 60-inch to classify, and to other telescopes to go deeper if that's necessary. But you see the science target, get very young supernovas because you're constantly watching the sky, fast decaying transients like brown dwarf eruptions. And yes, everybody knows this by now. That's kind of an old point. Yeah, everybody has seen optical transients of gravity waves. And in a sense, a system like this that can rapidly survey the sky and look for things that change, they're a discovery engine. They're constantly surveying, discovering new things that can then be exploited by the large telescopes. And this is just some nice pictures. You can imagine what they're doing. They're taking a new image. Look at the sequence. They're taking a new image. It's kind of a little bit grainy. You can see two objects there. You go look up a reference image, pull it up, do a subtraction. Yep, there's some different things and so forth. We think that that's a new object. Cue it up to go to the 60-inch. And just for fun, the old Palomar transient factory that was the predecessor of ZTF, you see M101, and lo and behold, there is a supernova. I think that's from 2011, and you see the little supernova, the little dot in one of the galactic arms, and it really helps that you get the green arrows showing where it is. Oops. And there is a modern ZTF image of M101 that just gives you an idea of the scale of the imagery and the amount of detail. And since we're all, they like to present it this way, but we as amateurs kind of like to see the reverse. This is a group, I think, from Claremont College in the next to the 48-inch. You see, it's kind of an unusual view because the base, the covering is off the telescope right now, but they give you an idea of the size. This is from last week. Some familiar faces next to and the rear of the telescope is on. You see this big box, that's a whole bunch of computer controls to operate the system. And a couple of diagrams. I won't go into a whole lot of detail because we just don't have the time to do it. But there's an electronics rack, and cleverly enough, there's a filter storage unit that is accessible from inside the tube. And there is an industrial robot in here that can actually take the filters off of the camera, stow them, get another one, put it back on. It's kind of a clever device. And it was kind of brilliant to use an industry standard machine, although they had problems with cooling. Factory robots aren't designed to work at the temperatures at Palomar. So they had to solve that problem. Another good view of the magazine and the robot, but yes, it's baffled. And there's the robot and how it would lift these large, very large, I think the filters cost about $100,000 a piece. So it was obviously of huge concern that the thing be adequately tested and adequate latching and controls so that it wouldn't drop any of the filters, not just break the filter, but maybe drop it on the mirror. The Palomar 60 is the other part of the ZTF system. That's one of the Caltech professors talking to some of the docents and his class about it. Gives you an idea of the size of the 60-inch f8.75 rich accretion telescope. And it's got kind of a unique instrument on the back of it. It's one of my favorite instruments. It's called the SEDS machine, spectral energy dispersion machine. That's a close-up from last Saturday. That gives you a little bit of an idea in situ what it looks like. And the criterion that it's based on is the factory model. We've got to do just enough work to do an initial characterization of the object that's been presented. And the science goal was to be able to do this level with exposure times of under an hour. And I think it's much less than that. It's 20 to 40 minutes, depending on the particular image and the brightness of the object and so forth. Low cost and very efficient. And our friend from Mount Laguna Observatory, Robert Quimby, was on the initial team of 3 or 4 people who built the first version of that. And it was so successful, then they decided to rebuild it and make it a regular professional instrument. And what it does is it has what they call a rainbow camera. It's got 4 different filters, UGRI, if you're into the filter head world, simultaneous filters, so you can do filter spectroscopy, and it has a spectrograph or an integral field unit with a fairly low resolution. Remember, you're just trying to get an initial, what is this? Is it a supernova? Is it an eruption? Is it something else? So a real low resolution spectrograph, because again, the criterion is classification within a very short time window. There's the Palomar story, kind of in a nutshell. Pioneering design and engineering, and there's a little bit of the Palomar story that gaps what Steve presented and what I have, because even building this massive telescope requires the development of whole new technologies in telescope design. The mirror is just one part of it, the structure to maintain collimation with all this huge weight or others. But so in fact, it was a revolutionary design telescope at the time, carefully maintained through the years by Caltech. It's alive, new state-of-the-art instrumentations, and it's really the front end of this new paradigm of machine learning that will help us exploit the complex data that this telescope and other large telescopes are beginning to collect. Just for fun, if I got 5 minutes, we do this for the Caltech students, and we might transition from a Canon DSLR maybe to a ZWO camera or something like this. But the whole idea was give the students eyepiece time, but eyepiece time with 30 people queued up with one large telescope eyepiece. You know how long that would really take and how few objects you could see. But after there've been sufficient eyepiece observing, then you can put a simple Canon imaging camera on and go more rapidly and show them more things. And this has been fun over the years, and I can just give you a couple of, this is, I believe that's M1. You see how spread out the stars in the cluster are. There's the ring. There's M104 sideways. And my favorite one is M87, the elliptical galaxy. You can actually see the jet. You can actually see the jet coming off that. And we got that in a 30-second exposure with a 60-inch telescope. So that gives you some idea. I'm not going to go to the backup. It decided to go to the backup without my intervention. But that's just a Russell Porter sketch from 1936 about how the telescope would work. I'll just point out one. Steve mentioned that there are different optical foci. There's a shell spectrograph in the east arm. There you see this baffle tube that leads down to the point G, which is Cassegrain focus, and there's a cage there now. There used to be some pretty weird ways to use Cassegrain focus, swing, kind of a swing-like affair, and there was a lifter that would lift the astronomer up. Of course, prime focus, and then you can send the light down through the south yoke into the Akude room, and that's where the deep space optical communications experiments being run. But just to give you a final little notion of size, you see area B, and above it is the real focal plane where there's a little glass photographic plate. This tube is 6 feet in diameter. In the old days, the astronomer would ride that telescope and change plates and operate a guiding instrument. So that's all I have. Admittedly, a very summary and very quirky, but that gives you an idea of some of the things that Palomar has done over the years.
Couple of quick questions. Ken came in over the
I'll
chat.
stop sharing if I can. Well, maybe I don't have to. Go ahead.
Couple of quick questions. Rob Roth asked, how fast can the ZTF slew?
I don't know how fast it slews, because between images, they may not, depending on the search pattern, but depending on the duty cycle pattern, they may not have to go very far. But I don't know the actual slew rate.
Can one of you go ahead and just bring everybody up to date on the tours? We've had a couple of questions come through specifically about the tours that are starting up on the 10th.
We'll have tours. Steve, I suppose we're going to have the same time that we used to have, 11, 1, and 2. Steve's gone.
No, he still sitting there.
I think that one's your call, Steve.
Late at night. Public tours on Saturdays and Sundays, 10:30, 12:30, 2 o'clock, and we reserve 9:30 for Boy Scout tours and things like that. Those will start November 10th. And, at that point, special tours for, well, let's say for astronomy clubs, for example, could be scheduled, just finding a time and date to do it. It is very difficult to schedule tours after 3:30 in the afternoon. That takes something special. Usually have to do the tours during the day.
Somebody asked what the smallest diameter telescope that you can put an AO on. And at least as far as I know, it's the AO devices are made specifically for the 200-inch.
Yeah, that was designed, and it's way too expensive for, that question begs amateur sizes. SBIG, doesn't SBIG make one for amateur telescopes? It's not, it does, it's a more of a tilt system rather than using a full deformable mirror like the advanced systems do. But I'm sure you could use that on a regular amateur instrument, and you can probably correct down 40, maybe 40% of the performance of a large system. Tip tilt is a pretty big component, I believe, but I'm not that much up to speed.
If we can reserve book a tour from the astronomy club, then how many members shall we have? What's the minimum number of people we should have to book the tour?
I don't know that there's necessarily a minimum. I'm permitted to have a maximum of 30 people on a tour, and I need a minimum of 3 docents to support that tour.
And both King and you talk about a lot of very cool instruments in the observatory. I just wonder, if we take the tour, then how many of them can we see?
Well, we'll be able to see what's on the scope that night, and maybe an instrument bay might be open, but probably not. So yeah, I on the tour, I think you more get an appreciation for the massive size of the telescopes, more of the engineering of the scope itself. You'll certainly get an idea of how it moves from the models and so forth that we have. And And you'll get to see everything in the basement. You'll get to see the foundation of the scope. Steve mentioned that there are two pressure chambers for illuminizing it. There's the small one down in the basement, and there's the large one that takes the 200-inch mirror. So yeah, you'll see a lot of worthwhile things, but again, doesn't really emphasize the instruments except to talk about what's on the scope that night and what they're doing.
Just from a personal experience, the first time you walk into the basement, you're dumbfounded by the size and the fact that this whole thing was put together in the 1930s when we were building battleships. And as you walk around and watch things, you will just be stupefied.
I can totally understand, and also from Steve's presentation talking about when the people, even the kids take off from the school to watch how the 200-inch, only the glass transport, and actually I can feel like those excitement sounds like very similar to recently, like when people talk about the James Webb telescope. I can feel the excitement.
Yeah. This was a huge advance in instrument capability when it was. And by the way, the slides you're looking at, if anybody's noticed, the mirror's not on the scope. What you're seeing there, you're seeing the bottom of the baffle tube for Cassegrain, and those black structures are the mirror covering that they lower and interlock to protect the mirror until it's actually being used. But notice the mirror is gone. It's in the illuminizing chamber.
Well, can I take a contrasting view? I mean, this was very much a revolutionary, a breakthrough, an advanced telescope when they made it. But you could also argue that it was something of a dead end, in that this is the last major astronomical telescope built on an equatorial mounting. This was the largest effective telescope in the world from 1949 until the first of the Keck telescopes came online in 1993. And the reason Palomar was the largest effective telescope in the world for such a long time is that they could not build a larger telescope until they had the computer controls to mount telescope in azimuth. They could not build a larger telescope on this design because the weight considerations. The weight goes up, I don't know, geometrically or exponentially. The moving parts of the Hale telescope weigh 530 tons. A 300-inch telescope would have, the weight would have been prohibitive. They couldn't do it. And so to make a bigger telescope, they had to go in a different direction.
And of course, above a mirror of about 8 meters, this is a 5-meter mirror. University of Arizona could make 8-meter mirrors. But if you go larger than that, then you're going to have to segment the mirror, make them out of big hexagonal glass plates, and have more advanced computer systems to hold the figure. This has a passive system, passive mechanical system to hold the figure of the mirror as the telescope moves and puts different stresses on it. The mirror is so heavy, and glass by its very nature would tend to sag and flow. So this is the first telescope to use that kind of technology. But of course, in the 1940s, they couldn't use computer-driven actuators. They had to use, big, heavy mechanical systems that still work well. But that's probably another example of a technology that really wasn't going to go anywhere.
Oh, other things.
Any other questions? I think we've exhausted them.
Exhausted me.
Is there anything in the chat? Okay. I like Gracie's comment. Caltech can sell every man behind the curtain. Why aren't Annette Brown, why aren't amateur astronomers ever allowed to utilize the telescope? Yeah, the man behind the curtain. Well, there's no way for us to really intervene in the process because it's done competitively with bids from institutions that have donated money to have the right to allocate time.
Donate, that's interesting term, donated.
Well, yeah, it's a, yeah. Would it make sense to improve the 200-inch surface now with the improved imaging equipment? I don't know. Theoretically, University of Arizona could make a better mirror. They use CNC machines. They could make it definitely faster. They might be able to have a better service. But I don't think there's any interest in redoing it for the huge cost. One of the advantages of this telescope, when you looked at the man behind the curtain, cost of use of $13,000 per night, is you get that kind of a price on a big telescope like this because it's been totally amortized. So if you build a big new fancy telescope like Keck or Subaru or any of them, you're still having to pay off the loan. So it's going to cost you quite a bit more. If that new telescope and maybe more aperture is worth it, then you just have to bite the bullet. But if a 5-meter telescope that works as well as this meets your science requirements, it's obviously the preferred choice.
Yeah, the basic cost of, I think Steve told us last weekend that the cost of using Keck is someplace in the neighborhood of $150,000 a night or something along that line, or at least north of that amount to use Keck and some of the other telescopes. So
Bill
this
Blank,
thing,
I'm sorry.
yeah, so this thing's a real bargain compared to other telescopes around the world as far as being able to do research.
Yeah.
And we get more requests from professional astronomers. We get more requests for time on the telescope than we got nights to give out. And we need all the nights we can get because that's what pays the bills around here. The astronomers are our customers, and their institutions pay the bills, pay the fees for each night's observing. And we got to cover our costs.
Bill Blanco noted that you can see the M87 jet on the Palomar Sky Survey plates. I didn't really know that, and nobody noticed it at the time. I
have seen it. I can't, unfortunately, I can't remember whether it was the blue or the red, but as a graduate student, when we were being introduced to the copies of the Sky Survey at the Royal Observatory, Edinburgh, somebody got out a jeweler's loop and yeah, we took a look. They said, check this out. And there was the jet. So it shows you why you need automated analysis of images, because otherwise, if you just leave it up to humans, we'll miss stuff out. All right. Sorry to interrupt.
Oh, no, that's a good point. And by the way, while we're on that, the plates for the ZTF are available online too. They are processed at the Infrared Processing and Analysis Center on the Caltech campus, IPAC. So if you Google that IPAC, you will find a system that will, fill in the blanks that you'll have for a given object. You're going to find lots of plates that have this object. So you'll just have to select, one and download it. I think they give it to you in JPEG or FITS. And I think what the mechanism is, they periodically make a data dump on the public access site. But yeah, you can get pretty recent stuff from the 48.
And I guess they'll have to use AI to filter out all of the Starlink satellite tracks, unfortunately.
I'm sure they will, but they should be pretty obvious, and they'll be more pronounced, you know, at dawn and dusk rather than the middle of the night. Aziz recommends The Perfect Machine, which is really an excellent book, and it covers a lot of detail. I think they have it at the gift shop at Palomar, but Amazon certainly has it available in a Kindle format. If I had $13,000, Bob Roth, if I had $13,000, what size eyepiece should I use? You know, we've done calculations, you know, because we put amateur eyepieces. A 31 pan would work well on the 60. With a 200, you know, a 31 pan is going to give you, when you work the numbers, it's going to be like 800 or 900 power. It just, but yeah, if I had $13,000, you know, I think if you had $13,000 and, you know, you didn't have any family or any dependents, you might buy a solar scope.
Kind of think about that.
Thank you, Ken. I appreciate that. Now, if I just need the 13,000.
Well, I don't think it costs the whole 13,000, but you know, the darn things are so expensive, and you know, well, we're at a good spot in the sunspot cycle, and there is the eclipse coming up, so it's just hard to part with that much money for something that's so specialized.
So true.
Can I ask a historical question? And I'm not trying to stump you guys, but who was the last person to ride in the prime focus cage? Lucky enough, when I was at UCSD, I got to hear stories from the Burbages, Margaret and Jeff, about riding around, and it sounded like a lot of fun. But I'm just curious, who was the last person to do it? And is the cage still around, or in a basement somewhere?
Well,
Oh no, it's still on the scope.
Oh, that's right. Yeah, it's still there. But
Yeah.
who was the last one to go in and I guess drive it around while it was taking photographic plates?
I don't remember the name of the astronomer, but the last photographic plate was used on this telescope in 1989. Some Caltech researcher wanted to reproduce images that he or she had made years before, wanted to be able to check them. And so they ran a run that did photographic plates, and that person drove the telescope from the prime focus cage, even though the telescope had been digitized 10 years earlier. I don't remember the person's name.
Thank you. That's cool. Up as late as 1989. I did not know that.
And yeah, the prime focus cage certainly is still there. The curved floor is still there. The floor that they used to ride around as the telescope moved back and forth. And in the archive, we have the seat. Talk about trivia. We have the seat of the chair that used to be up at prime focus. There isn't a chair up there anymore. It's all filled with equipment. There's no space. They still go up there to maintain the instruments, but yeah, nobody's up there all night anymore.
If I'm not mistaken, last month's speaker had an instrument that was mounted at prime focus. Wasn't that the case, Ken?
Yes, he did. Was that Chimera?
Yeah, it was a she, and I think it was, yeah.
Yeah.
And so there's quite a few instruments that are still used at prime focus.
Oh yeah, well, obviously either a near infrared or visible light like WASP, the wafer scale
Yep.
imager, and Chimera still goes up at prime focus too. Chimera is, I just couldn't show all the slides. I figured, death by slide, but it's a pretty clever device that will take fairly rapid imaging. It actually incorporates some Canon, 200 millimeter f2.8 lenses, which I think is pretty clever, even as expensive as they are. It's nicer to use something that's off the shelf manufacturer than building your own optics. And yeah, but that's used for things like Kuiper belt transients and things like that.
Peter wants to know at f3.3 is a giant coma corrector used at prime focus.
Yes.
Yes.
We have what's called the Ross corrector that's installed up there. Ross corrector was first, that was replaced a couple of years ago. It's now the WYNN, WYNN corrector, and it's used on almost all observing occasions at prime focus. There's also a field flattener that can go in at Cassegrain focus. Cassegrain focus is normally f16, but with the corrector in place, we can run Cassegrain focus at f9. And if we really want some magnification, you can do Coudet focus at f30.
I think it might be it. I'm not seeing a whole lot come across. I think we're getting close. Anything else? Anybody?
I guess not.
Well,
Well, Steve, thank you so much for that historic information. I've seen the predecessor of that presentation, and you've just done wonders with it. Especially including finding all those old videos and putting them in. That was just great.
well,
Thank you both. It was a great presentation.
and thank you. Hey, I really appreciate. Thank you for asking me to be here. And I thought tonight was a whole lot of fun. I enjoyed the discussion very, very much. So I'm going to sign off, and I've got operations meeting at 7 o'clock here. I'm going to go home, get some dinner, go to bed, and thank you very much.
Thanks
Bye-bye.
for
Thank
being with
you.
us. Bye-bye.
very
Really
much.
good presentation. Really good.